This is lecture 13 of Machine Learning and Bayesian Inference. I finished the last lecture by just starting to talk about unsupervised learning. And the overall idea here is that I simply give you a whole bunch of vectors, feature vectors in the parlance we've been using all along, and your job is to infer whether in some sense they form clusters. And at the end of the last lecture I explained the operation of the k-means clustering algorithm, which is a long-standing algorithm for doing this job. But what I want to do today is talk in detail about how you might derive an algorithm for clustering within the probabilistic kind of framework that we've been dealing with. Now, in order to do that, I'm going to introduce something called the Expectation Maximization algorithm, or EM algorithm. And this lecture is one that you may not fully appreciate the first time you see it. With quite a lot of the material in this course, I think it's just about possible to give quite an intuitive explanation regarding how someone might have come up with the ideas in the first place. I find that much trickier with the material in this lecture. It always strikes me, looking at this material, that it looks as though it was sort of conjured from nowhere, essentially. And it all fits together. But giving a step-by-step coverage of the EM algorithm that looks as though it's a story of how you might have come up with it in the first place, or of how its inventor might have come up with it in the first place, is much trickier than in, I think, all the other material in this lecture course. So, this will look a little bit like magic the first time you see it, but it's mathematically it's appealing and relatively straightforward. There's just quite a lot going on, and so for that reason as well, you may not you may not appreciate this at first sitting, and you may have to actually study this lecture a bit to really understand and to follow everything that's going on. But with that warning well and truly made, let us bravely continue. When I spoke about supervised learning, I started off by giving you essentially a thought experiment. I was saying, let's make a model for this data, and I know what the model is, and I use it to generate some data, and my model has parameters. But I don't tell you what the parameters are, I just show you the data. Can you work out what the parameters were? That's essentially maximum likelihood. I said, with maximum likelihood for regression, I have a model. Maybe it's polynomials, maybe it's a neural network. Whatever it is, it has parameters attached to it. And there are some feature vectors, and I choose my parameters for my model, and I pass the feature vectors through the model, and that gives me some labels, and I add some noise to them, and then I show you the data that I've generated in that way, and I ask you to infer what the parameters of my model were. Well, maximum likelihood estimation says, if you know what the structure of the model is, if you know it was linear or a polynomial of a specific degree or whatever, then find the parameters for which the probability of the data given the parameters is maximized. And we want to put unsupervised learning into a similar kind of framework. So on this slide I'm proposing a thing called a mixture model, which says that if we assume that our data comes from K clusters, has been generated in such a way that it should form K clusters, let's use a probabilistic model that looks like this in order to model the generation of that data. And all this says is that if I have K clusters in order to generate one data point, I first roll, let's say, a k-sided die, which doesn't have to be fair. In fact, the probability that it comes up on its kth outcome is pi sub k. Okay, and then for each of those k outcomes, I have a probability density p of whatever that models that specific cluster. Okay, so I roll my k-sided die and it says use cluster 2, and now I have a probability density that models that cluster, and I sample that and I get a vector x, and that is the first vector in my training set, and I do this multiple times. Okay, and that gives me a collection of data that will have a more or less kind of clustered look to it, depending on what probability density I'm using for each cluster. Now, as is so often the case, what I'm going to do here is use a Gaussian density for each cluster. And the clusters differ in that the mean and covariance for their associated probability density can vary. Okay, so in this case, my probability density for any given cluster is just normally distributed. And my overall probability density describing the probability of some vector being generated, given theta, which is all the parameters involved, just looks like this. Okay, this is a straightforward expression in probability. Okay, it just says that in order to generate a vector x, given a bunch of parameters, the bunch of parameters includes the values for pi sub k, okay, the individual probability of getting any specific cluster, and the means and the covariances associated with a Gaussian density for each cluster is just given in the way I've described. Okay, you pick a cluster with the relevant probability pi sub k, and when you pick that cluster, you sample the Gaussian density in order to get your x, and that gives you one vector. Okay, the diagram on this slide is just an example of this process in action. Okay, the dots on the lower part, the x1, y1, sorry, x1, x2 plane are generated according to precisely this kind of probability density, this mixture density. It's a Gaussian mixture, and the surface that you see at the top is the probability density that I used. In fact, the density that I used to produce all the earlier examples of clustered data as well. Okay, and you can see rather clearly here that there are three Gaussian densities that have been mixed together, and their proportions are non-equal. And then the clustering, or the clustered nature of the data, comes from the fact that their means and covariances are different as well. So that's just a case of sampling this guy a large number of times. Each time I sample it, I get a different x, and that forms this data in the x1, x2 plane. So what next? Well, I can play exactly the same game as I've been playing all along. If I have m points that I get from sampling a Gaussian mixture m times, and the samples are independent and identically distributed, so we don't change the Gaussian mixture between samples, and each example is sampled independently, then the likelihood of the full data set of all m samples is just the product of the probabilities for the individual ones. And as is usually the case, we take the log because that turns products into sums, and we generally like sums more than we like products. Okay, so this is now the likelihood. You may want to backpedal at this point to some much earlier lectures where I defined the likelihood in the supervised learning case. Okay, but we're doing essentially exactly the same thing here. And we've taken its log, and taking its log turns this outer product into a sum. And then this expression here is precisely what was on the previous slide. Okay, so I emphasize again, this is a model for how data can be generated. And the name of the game, if I give you just the data I've generated, but don't tell you what the parameters of the model were, okay, the pi's, the mu's, and the capital sigmas, can you work out the values for those parameters, all collected together in theta here, for which the probability of the data, capital X, given the parameters theta, is maximized. Okay, that's maximum likelihood for this unsupervised setting. Now, having written down the log likelihood here, which is the thing we want to maximize, we immediately come across a problem, which I'm not going to work through in detail. So you can try working this out yourself directly, or you can take my word for it. This you can't maximize directly. Okay? If you try and differentiate this expression, set it to 0, and solve for the pi's, the mu's, and the sigmas, you'll find you can find stationary points, but they depend on each other, and that makes things very tricky. Okay, so we can't really get a closed form solution for maximum likelihood in this case. Okay, remember, for ridge regression and for just straight linear regression, we had a closed form solution, not here. So this then begs the question of how do we go about finding a maximum likelihood solution? Can we come up with a sensible learning algorithm? Okay. Well, the answer is yes, and the first thing we need is a concept that's going to be pretty important going forward. That's the idea of a latent variable. We're going to introduce some extra random variables corresponding to things that we can't actually measure. It turns out that introducing these gives us a slightly different expression that we can deal with, and it gives us an expression that's different in quite a useful way. First, I'm just going to mention this little diagrammatic notation here. This is quite common in dealing with the building of probabilistic models. I'm not going to use it a great deal, which is why I'm not going to really define it in its full generality, but it's worth just exposing you to it because it's fairly common. In this diagram, random variables appear in circles. If they're observed, then the circle is shaded. Okay, so x sub I, the ith actual vector, is something you observe. Z sub I, which I'm going to define in a moment, is not observed, so its circle is not shaded. Non-random variables, parameters in this case, are not placed in circles. Okay, hence theta, mu, and sigma. And the square that is drawn around Zi and Xi is denoting that there are m copies being generated. Okay. Now, the latent variables are simply indicators that, if you could observe them, would tell you which cluster generated which data point. Okay. Now, let's just emphasize that given only one of those data points, one of these guys here, it could have been generated by any of the three clusters. Okay, you don't know just from seeing the data point which cluster generated it. There is a non-zero probability for each of these individual Gaussian densities that it could have produced any of those data points at all. Okay, the Z variable is just going to tell us, if we could observe it, which we can't, which of the clusters generated each individual data point. So the latent variables, the zi's, and there is a vector z sub I associated with each data point. It's a vector with k elements, one for each cluster, and those elements are all 0 with the exception of the one corresponding to the cluster that generated x sub I. Okay, so the ij element in one of these vectors is 1 if the ith data point was generated by the jth cluster, and 0 otherwise. Okay, these simply tell you, or would tell you if you could observe them, which cluster generated which of the ith x's. So what can we now do, having introduced these latent variables? Well, the first step is to use the marginalization trick backwards. Okay, remember, this is something that I introduced right at the very beginning, and it's in the supplementary handout on probability. Usually with marginalization, you are trying to get rid of a random variable. But if instead of doing that process left to right, you do it right to left, you can introduce one instead. Okay? So that's what we're doing at the top of the slide here in order to get these latent variables into the picture. So the first line here, all I've done is written, well, precisely an application of that trick in order to bring Z into play. And then in the second line, I've just split the joint probability of x and z given theta into a conditional probability and a prior in the usual way. Okay, probability of A and B is probability of A given B times probability of B. Now, these are a little more tractable than the probabilities we dealt with before. Okay, because probability of X given Z and theta, now I'm asking what is the probability of a given point when I actually know which cluster generated it. Okay, it's conditional on knowing Z, the latent variable. And that is an easy thing to write down. Okay, it's just the expression for the probability density for that particular cluster. Okay, and I can write it using a similar trick to the one that I used again earlier in the course, as a product of each of those raised to the power of the relevant latent variable. Now actually this might look clearer, my apologies. I think it would have been clearer to have written these as x sub I, z sub I, and similarly here, because I've used the I subscript in the these raising to the power of these latent variables here. Okay, sorry, I hope that's not going to be confusing. Now, all that's happened in this expression is that I've said the product of these values for each of the clusters actually collapses just to the value for one of them when we raise to the power of the latent variable here, because the latent variable is only 1 for the cluster that generated the data point, and it's 0 for the others, and anything to the power of 0 is 1, so this product gives us exactly what we want. Okay, so that's just saying that the probability of the ith x, if I know the latent variables and the parameters in theta, is this product, which just collapses to the probability density for the ith x for the cluster that generated it. And similarly, for this, the probability of a particular latent vector, the ith latent vector, corresponds simply to the probability of selecting the cluster that that latent vector corresponds to. Okay. If I have a latent vector that is 1 at the position of a specified cluster, the probability of observing that has to be pi sub k for k corresponding to that cluster. And this expression is going to give me that, once again, because I've taken the product across all of the pi sub k values, but this is selecting just the one that I need. Okay, and multiplying those two guys together then gives me a probability for xi and zi, conditional on my parameters. Okay, so we can take this one step further. So essentially what we've done here is to say we're introducing these latent variables and they're not observable. But what would happen if they were? Haha! The diagram now has z sub I shaded in. What's the deal if we could actually observe that? And that's essentially what we've just been looking at. Okay, so from the previous slide, I put the two expressions that are circled together, and I get this expression for the probability of an x and a z, and my apologies once again, because it would be clearer if I subscripted I on these. What is the probability of the ith x and the ith z given the parameters? And we've just derived an expression for that. And then the final part of this slide just says, well, once we know that, we could write this slightly different form of the log likelihood. Okay, instead of probability of just capital X given theta, it's now capital X and capital Z. Okay, all the data and all the latent variables given theta. And because, once again, everything is independent, we just take the product for the individual guys. And written out in full, that gives me the final expression. Okay, that's just this guy plugged in here. Okay, so I've got now an expression for essentially a likelihood that would be useful if we could observe what the z's are. Okay, so we still need to make some kind of final connection between this likelihood for when the z's are observable and the actual likelihood that we're interested in. Okay, we haven't quite got that to that bit yet. Now, this is just a summary of where we've got to. Okay, the shaded box here has the expression from the previous slide. I've just taken the log through the two product signs, and then having turned the product signs into sums, I've used the log just to split this up into a couple of pieces. Okay, so the first expression there follows directly from the previous slide. Now, we started off by saying I want to maximize log p of x given theta, but that's intractable. So let's try introducing these latent variables, and now we've got this, which, trust me, is going to turn out to be more tractable. We just have to link them together. Now this is where it becomes very difficult to see how one might come up with such a procedure in the first place. Okay? This is all essentially just straightforward manipulations of sums and logs of probabilities. But it is very difficult to see how one might have invented it, and so it can look as though it just appears by magic. Okay, but let's just look at what it says. I'm introducing another new thing called Q of Z, which is any distribution at all on the latent variables. Okay, I emphasize it's an arbitrary probability distribution on the latent variables. Now, we have this expression, okay, which looks a bit unusual, but it's going to give us something quite fun. Now, I'm manipulating it into a slightly different form. In the first line here, I've just split, in the time-honoured fashion, the joint probability of x and z given theta into a conditional probability and a prior. Okay, that's what's happening here, and nothing else changes. In the second line, I'm using the log to split up the expression a little. In the third line, I've written the first chunk of that summation, okay, and I'm actually distributing that summation over this chunk and the chunk that results from taking Q of Z inside and putting it in front of that second part there, okay, which gives you this. The third line is giving me, well, this guy here, which I'll come back to in a second, and this expression. And this expression, well, it's a sum over z, and log p of x given theta doesn't depend on z, so we take it out. And then we've got the sum over z of q of z, and q of z is an arbitrary distribution, so it sums to 1. Okay, we're just left with log p of x given theta here. And this guy on the left is the negative, or something called the Kullback-Leibler distance, which I am very much hoping you have come across elsewhere, in particular in the information theory course. But if you haven't, don't worry. It's something that we can deal with in any case, but it is an extremely important measure. Okay, it has a special place in computer science and information theory, and it's something that comes in handy here. But we only need a couple of its properties in order to see why that is. Okay, so this slide, we start with this expression for reasons that will become clear in a moment. We end up with the KL distance between two distributions on Z, and this term, which, let's just remind ourselves, is the thing we're actually really interested in. Okay, this guy here is the actual likelihood that we want to maximize. So, we need to know two properties of the KL distance. It measures the distance between two probability distributions, and this is how it's defined. Okay, the negative on the previous slide comes from the fact that on the previous slide it has the form of log qx over px, not px over qx, and that -1 then comes out of the log and just gives us a negative. And the two properties that are important for everything that follows are that the KL distance is always non-negative, and that it's 0 precisely when the two distributions are the same. That's all we're going to need. So, what can we do with that? Well, I'm going to write the expression we started off with as L of Q and theta. Okay, that is the expression here. Okay, that's going to be the shorthand for that expression. And if we take that expression, L of Q and theta, which is equal to the thing on the last line, and we just rearrange, okay, that's all we're doing, we get this expression. Now, that should make us happy, because we know that the KL distance is always non-negative. And because it's non-negative, that means that the expression L of Q and theta gives us a bound. Okay, it gives us the bound in the shaded box. And we know that the thing we're trying to maximize is greater than or equal to L of Q and theta. And so that gives us a way of potentially finding a theta that will maximize the log likelihood, log P of x given theta. We can just try and maximize L. And we can make L as big as possible by iteratively maximizing with respect to Q and with respect to theta. And this is the expectation maximization algorithm. Okay, let me say that again. We want to maximize this guy. We now have a bound that shows us that by pushing up the value of L of Q and theta, we can push up the value of the log likelihood. So the strategy will be to iteratively maximize it with respect to Q and to theta, each time keeping the other one fixed. Okay, so we'll start with Q sub 1, theta sub 1. Okay, I'm going to introduce the subscript t, meaning which time step in this iteration we are. And we keep theta 1 fixed and update from Q1 to Q2, okay, by maximizing L while keeping theta 1 fixed. And then we keep Q2 fixed and we maximize with respect to theta to get theta 2, and so on until we get convergence. Okay, now maximizing with respect to Q is called the E step, expectation, and maximizing with respect to theta is called the M step, maximization, the EM algorithm. So the only thing that's left is to look at how we do this. How do we do this iterative maximization with respect to Q and with respect to theta? Okay, well, let's say that we're at step t in our maximization process. So we have qt and theta t. And the E step is going to be to keep theta t fixed and maximize with respect to qt. Now we know that we have this expression, and we've just derived this. And this actually tells us that maximizing with respect to Q is really easy, even though Q is actually a distribution. Okay, what we're actually asking here is choose the distribution on the latent variables that will maximize this expression. Okay, but that's fine. Why is this fine? Well, theta t is fixed, so the likelihood term is as well. Okay, this is a fixed value. The KL distance is minimized and equal to 0 when P and Q are the same thing. So if I want to maximize L, I minimize the KL distance, okay, because this guy is fixed, and we have this on the right hand side. If I want to make L as big as possible, I make dKL as small as possible. Making dKL as small as possible would make it 0, and that happens when P equals Q. Easy. Okay, we just make Q equal to P. What is P in this case? P in this case is as shown in the final shaded box. Okay, if you look back at the derivation of this expression, you'll find that the P we need is the probability of the latent variables given the x's and our currently fixed value for theta t. Okay, so we immediately get the distribution that we want for that step, and that's straightforward. What about the other step? Okay, well, this is a little more involved, but not hugely so. For the M step, okay, we now write L of Q and theta in its full form. Again, this is derived directly from a couple of slides back. All that I've done is use the log to break up the expression and then distributed the sum over it. Okay, this is L of Q and theta. I can use the log to break that into a sum and then distribute the sum over z, Q of z over the two components of the sum. And I get the first line on this slide. Now, the second term there doesn't depend on theta. Okay, I'm keeping Q fixed and I'm maximizing with respect to theta. So I don't care about this guy. And what about the first? Well, we've just said that we are fixing the t+1th value for Q to be a specific distribution. Okay, that was the previous step in this iterative maximization process. If we plug that result from the previous slide in, then we have the expression in the shaded box. Okay, we're maximizing an expression, okay, that is maximizing L, which is the sum over z of QZ, which is the one we've just derived, multiplied by log of this kind of joint likelihood. Okay, which gives us directly this expression, and we can also write that as an expected value. Okay, sometimes I think it's easier to think of things as expected values. We're actually interested in the expected value of this kind of joint likelihood with respect to, well, Q in fact, the Q at time t+1 that we've just derived. And that's nowhere near as scary as it looks. Okay, why is this nowhere near as scary as it looks? Well, if we look at the actual expression for what's in the brackets here, again, we pull this from a few slides back. This is what it looks like. We're wanting to take an expected value of that expression with respect to a distribution on Z. Well, that expected value is going to go through the sums. This doesn't depend on Z, and so we actually only need to work out the expected value of Z. Okay? Now, there is just one extra thing to point out here, which is that we're now updating theta from theta at time t to theta at time t+1. Theta is the collection of all the parameters, all right? So these guys actually have a time index on them as well. Okay, but I'm leaving that out so that things don't get cluttered. Okay, we're actually maximizing over those at this step. Now, the next slide is really just summarizing again what I've just said. We're taking an expected value of the expression in the first box. Okay, we're taking the expected value of this whole guy here. Well, that expected value goes through those sums, and this guy doesn't depend on z, so we just need to look at the expected value of z. Okay, so it's actually only this that we need to worry about. And that comes out quite nicely as well. So what have we got on this slide? Well, the first line of this little derivation here just writes the expected value out in full. The second line says that if we're summing over all possible values of capital Z, okay, remember capital Z has a Z sub I in it for each data point, and we're summing over all of those, okay, so we can split that sum into a sum over each of them. Okay, that's what we've done in the first line. Then we're saying that only one of those sums involves the actual ith z vector here. Okay, so we will end up marginalizing out all the other ones from this part of the expression, which is what gets us to this point. Okay. Or another way to think of it is that this will come out of the sum for every sum except the one that's summing over z sub I. Okay, and those will then marginalize out the corresponding z's here. Okay, so we end up with just the ith one. And then we can marginalize again. Okay, because the zi, this is now a sum over the k elements being set to plus or minus 1 for each element of zi, and only the kth one of those is of interest. The others will marginalize out, which gets us to here. Okay, so we're just summing over the two possible values for the indicator for the ith example and the kth cluster. Those values are 0 and 1, and we've just ended up with this for the expected value. And because that's an indicator random variable, it's only 0 or 1, it's actually equal to the probability that the ith vector was generated by the kth cluster, but now conditional on actually knowing the data and the parameters. Okay, so there's not much more of this to go now. We're nearly there. I'm sure you'll be glad to know that. What can we say about that expression? Well, the first thing to note is that in this probability here, we can say something about conditional independence. Okay. I'm going to talk a lot more about conditional independence later, but for now, I think it is sufficiently intuitively obvious that we can say this, that I will hope that that stands up. Conditional independence just means that if you have an expression like the probability of A given B and C, it would just collapse to the probability of A given C. Okay, this is conditional independence. we have conditional independence here because the probability of one of these indicator variables, given that you know the training data and the parameters in theta, well, knowing all the training data is no different to knowing just the ith one in this case. Okay, we can say that the probability of zik being 1, given all the data, capital X, and the parameters, is equal to just the probability of zik being 1, given the ith training vector and the parameters. Okay? Now, if I then turn that back into a joint probability, I get the second line. Okay? Because the probability of A given B is the probability of A and B over the probability of B. And now I have this nice expression. Why is this a nice expression? And where does it come from? Well, on the top, the probability of generating the ith training point in the kth cluster, because these are two independent processes, okay, the probability of getting the kth cluster is just pi k, and then independently of that, I go to the density for the kth cluster and sample it to get xi. That means that I've just got this expression on the top here, okay, for the joint probability of xik being 1 and xi. And on the bottom, well, that's just the definition that I started off right back on basically the first slide, where I set up the probabilistic model for a Gaussian mixture. Okay, that's just the definition written down again. And that's now looking good, because if I write it as a shorthand, okay, using this gamma notation here, and plug it back into the expression that we actually want to maximize, the only things that appear in the final double sum in this final shaded box are actually expressions that involve the parameters that we want to maximize over. Okay, so theta contains the pi's, the mu's, and the sigmas. And now I have this expression for the gamma, which appears in here, and this whole expression now just has the parameters of interest in it, and we want to maximize over those to get the next theta. So now we've got back to a standard maximization problem, and in this case it's tractable, so we can differentiate, set to naught, and solve. And that part is an exercise. Okay, I'll just say a little bit more about that in a moment, but let's just summarize what we've ended up with here. Summary of the whole lecture. I set up a probabilistic model for the generation of a training set, capital Z. Okay, and then I said, in the maximum likelihood way, we can say what is the collection of parameters that maximizes the probability of a data set given those parameters being used to generate the data we see. That's easy enough to write down, but we can't just maximize it directly. Doesn't work out. So then I introduced a new arbitrary distribution called Q, and that gives us a lower bound. So we try and find a good value of theta, okay, that will maximize the right hand side of that bound by iteratively maximizing L on the left hand side of the bound with respect to Q and theta, at each stage holding the other fixed. And that tells us that the E step, the maximization of the Q part while theta is fixed is achieved using this distribution. And then, when we're keeping Q fixed at that distribution and maximizing with respect to theta, we need to maximize the expression in the box. Okay, so that in a nutshell is what we've arrived at. Okay, so the final thing is to derive the M step, and you do this by differentiating the expression in the box here, setting to 0 and solving. But there is one further point, and that is that because the pi's have to be a distribution, that's a constrained optimization. Okay, the pi's have to sum to 1. So for the mu's and the sigmas, you're differentiating, setting to 0 and solving. But for the pi's, you're differentiating, setting to 0, solving, but you're introducing a Lagrange multiplier to make sure that those values end up summing to 1. And if you do that, and this is an exercise to complete for your supervisions, you will find that the solution is given by the updates in the final box on this slide. Okay, so you know what answer you're aiming for. So, that is a lightning introduction to the EM algorithm. And what you have on this slide is a bunch of update equations, which you can iterate in order to fit clusters to data. The EM algorithm is way more applicable than this. Okay, it is extremely general, and it allows you to solve these kinds of problems by introducing latent variables, and latent variables are surprisingly common. Okay, they're often something that you can introduce quite naturally. In this case, they're very natural to introduce. Okay, because you can just say, well, imagine we knew which cluster each data point came from, and then you apply the EM algorithm. Okay, and it's quite often the case that it's equally natural to do something like that. So as a final slide for this, before I move on in the next lecture to talking more generally about Bayesian inference, here is just a quick example of what happens if you apply this EM algorithm to the data that I've been using as an example. So the light blue dots here are the data set that I've been using. The first upper left slide shows a somewhat arbitrary starting point of 3 clusters with very similar means and very similar covariances. And the top right shows what happens after the first iteration. Okay, clearly that first iteration is enough to jump the means to somewhere in the middle of the data, which seems sensible, and to expand the covariances out so that they kind of capture a more natural extent for the data. So that seems good. And then at the bottom we see what happens after 10 and 50 iterations. After 10 iterations you can see that the means have spread in order to start identifying these 3 clusters, and the covariance matrices have been updated to better reflect the structure of the data, and after 50 iterations both of those points have been further emphasized, and we're getting means and covariances that taken together look like a decent model of the data that we started with. Okay, so like I said, there's a lot in that lecture. You may have to look at that a couple of times, and to understand it you really do also need to work through it and to work through the full derivation of the rest of the M step. Okay, but I think you can have some fun with that.